Alright, so this is our first tutorial on refraction. We're going to define refraction and look at why it happens and introduce an important measurement related to refraction, that's index of refraction. Future lessons will deal with how much something refracts and look at the conceptual aspects of that, and then ultimately another phenomenon, total internal reflection. So we're going to build off the idea we saw from the demonstrations we saw in class in regard to when you're looking at the coin that appeared when it was initially blocked by the lip, or watching the light coming from the fish tank and how it distorted images. We mentioned before that all those had in common was this concept of refraction. So let's define it and just talk about why it happens and then do some example problems with it. Okay, so like reflection, refraction is the bending of light. Okay, and the bending of light, or any wave for that matter, isn't because it's bouncing off a surface, but that's reflection. It's because it's entering a different medium. Okay, and so for light, this would be a transparent medium, entering glass, entering plastic, diamond, oil, or leaving those media. If we're talking about other waves, such as sound, a change in medium doesn't necessarily have to go from air to water, which it could. It could also ultimately be differences in temperature or differences in depth. And we'll talk about what medium does in terms of the actual measurements of the wave in a second. The second criteria, besides entering another medium, is it has to enter at an angle. When we talk about an angle, it's got to be from the normal. Okay, we always measure angles with reflection and refraction from the normal. So here is an illustration of a refractive event. You got parallel wave fronts coming in, they hit a boundary right here, along here, and then we see that there is a change in a wave. Notably, there's a change in the trajectory or the angle which is moving, and if you look close, you also notice that there's a change in the wavelength. And we've discussed this before. When a wave goes from one medium to another, it will change speed, change wavelength, but now we're also seeing that it will change direction. So if we try to represent the ray, which we'll most commonly do, is we go perpendicular to the wave fronts, and here I'm going to draw it at the point where I've drawn a normal, so this is our incident angle. And then we see that the rays, if we keep perpendicular to our wave fronts, are change direction, and this would be our refracted angle. And we'll learn about how to calculate this given this and something about the media in the next lesson. But the point is right now that the ray is changing direction because it is entering in a medium, and there are two factors that determine how much it refracts. Okay, one is the angle of incidence. Okay. In other words, if we have a ray coming straight into the water, such that the angle at the normal is 0, there is going to be no refraction. If we come in at a moderate angle, as shown here, you'll get a moderate amount of bending. And if you're coming at an extreme angle, such that it's almost 90 degrees, we would see the greatest amount of refraction. Refraction will never bend past the normal, but the greater the angle of incidence, we will see the greater the change in its deflection. The other aspect that influences it is the difference between the two media. And really what it's about is the difference in the velocity or the speed of the wave in each medium. Okay, and this is measured indirectly. So if light in air travels one speed and it travels at a different speed in water, there's really a ratio between those two speeds. And we can use those ratios, or the ratio between any speeds for any two media, to come up with an index for the speed. In other words, a number that reflects the speed but not give the exact value. And so an important measurement that's related to speed is exactly that. It's given a symbol, lowercase m, and it is called the index of refraction. And these values are usually given in a problem, but they are also in your Regents reference tables. So let me just state this now before we look at refraction a little more. So by definition, n is just an index. It's an indirect measure of something else, and it is equal to the c over v. C is the speed of light in a vacuum, or air for that matter, it's close enough, and v is the speed in whatever medium you're interested in. So if I've got light in a vacuum, c, and the speed of light in a vacuum is also c, the index of refraction of a vacuum is 1. If I look at the speed of light in air, I will see that the ratio of these two is just a little bit over 1, 1.0009 to be more exact. For all intents and purposes, the index of refraction of air is 1. If I have light in, let's say, water, where the speed was, let's say, 2 times 10 to the 8th meters per second, then if I take c, which is 3 times 10 to the 8th divided by 2 times 10 to the 8th, I get 1.5, which means in that particular medium, the light travels 1.5 times more slowly in that medium than in a vacuum. Okay, so let's look at why entering a medium at a different angle would give you a bending effect. So an easiest analogy to look at is with soldiers or a marching band marching in formation. So if you look at the diagram here, we have evenly spaced rows, which represents a wavelength of some sort, and the marchers are all marching with a common frequency. So we have two media right here. Let's say this is asphalt, and let's say this is mud. Okay, where we'll have an extreme change. Right. When the marchers enter the mud, their frequency is still going to be the same. They're very disciplined. They're going to move their legs up and down with the same rate. But because the mud is stickier, they're not going to be able to advance as far per cycle. So you can see two things happening. Visually, you can see that their wavelength has gotten less, right? They're a little closer together because they're not going as far. In other words, their speed has gone down. That should make sense. When you enter a asphalt and mud, you're going to go slower. But why would you turn is a little bit more subtle, and that's where the angle part comes in. So if you look at this boundary right here, where the first person in the formation hits, namely this person, he or she, when upon hitting the mud, are going to go slower, but these guys who are still marching with the same frequency are going to cover more ground because they're still in a faster medium. So if they travel a little further than this person does, there's going to be a natural turning effect. So if you look at that ray versus that ray, we see, well, my drawing isn't very good, that they're not quite as parallel. And if we go to the next cycle, right, they're even less parallel to each other. There is a bending effect between those that are in the faster medium versus the lower medium. Okay, once they're all in the medium, then they start moving parallel to each other and move off in a straight line because they're all moving at the same speed. So refraction can be explained using a physical particle type model. So we also mentioned that there's a speed change and that there is a wavelength change. So let's look at that right now. How we can determine the amount of change based on two indices of refraction. So let's say I represent the two media as an index of refraction, which is an indirect measure of the speed. What I can say very simply is if I do the ratio of the two indices of refraction, that's going to be by definition C over V1, which is, and this will be C over V2. Okay, so flip and multiply, we see that the C's cancel out and we get V2 divided by V1. So the ratio of the indices of refraction is equal to the inverse ratio of their speeds. Now if we apply the wave equation, we know this is equal to lambda 2, the wavelength in the second medium, multiplied by F2, and this one would be lambda 1 divided by F1. Going back to what we learned about waves in general, and light is no different, the frequency of the wave depends on the source. Okay, in this case, the marchers, that's just what the beat is, what they're supposed to be marching to. So when they enter the mud, that doesn't change. So F1 and F2 are the same, and so they cancel out. And this would be true of light. So we get another relationship for the ratio of the wavelengths. So going back to our equation, we can write in here then N1 over N2 equals V2 over V1, which equals lambda 2 over lambda 1. So that's an important ratio that is utilized. Okay, so let's look at an example problem and finish up here. Alright, so in the diagram on the left, referring to this, where we have rays coming in, we have medium 1 is air, and we're entering water. Okay, and we want to be able to predict, not so much the angles yet, we'll do that later, how fast the wavelength and frequency in water compared to in air, knowing the wavelength. Okay, so let's take the first one, the speed in water. if you looked up in your Regents reference tables the index of refraction of water, you'd see that it's 1.33 and air is 1.0. So we can say, based on the index of refraction of water equals the speed of light in a vacuum divided by the speed of light in water. Alright, so solve for the speed of light in water. And that's nothing more than c over the index of refraction, which is 3 times 10 to the 8th divided by 1.33, and I believe this is 2.5 times 10 to the 8th meters per second. Okay, so the speed of light in water is 1.33 times less than that of a vacuum. Very simple problem. Now, if we want to look at wavelength, we could use the wave equation, knowing the velocity and the frequency of the water, which isn't given, but we could figure it out, or we can use this ratio. So we'll go with the ratio because we have all the information. So I'm looking for lambda 2, so I'm going to say lambda 2 equals lambda 1. If I bring the lambda over to the other side, I can do V2 over V1, or I'm going to do N1 over N2, because those are givens. So that's going to be 500 nanometers. I'm just going to leave off the units. We started in air, that's N1. We entered water, 1.33. So if we do 500 divided by 1.33, we expect a smaller wavelength because our speed went down, and this is roughly 376 nanometers. Lastly, we want to find the frequency in water. All right, the frequency in water we can say is equal to the speed in water over the wavelength in water, in which case these are both 2. We can also do it for the speed in the air over the wavelength in the air, because the frequency is the same in both media. So if I go with the latter, because those were givens, this is 3 times 10 to the 8th divided by 500. Here I do have to convert the nanos, times 10 to the negative 9th, and I will get, I believe, 6 times 10 to the 14th hertz. You can double check that for yourself. Okay, you could verify it using this equation where we have 2.5 times 10 to the 8th divided by 376 times 10 to the negative 9th, and we should get the same answer. Okay, so that concludes this first lesson on refraction. We'll look at angles for the next lesson.